In this video we'll be using volumes of revolution, but this time we'll be looking at the shell method of evaluating the volume. Think of the shell method as though you're looking at a roll of toilet paper. In terms of the object that you're playing with, instead of slicing it in respect or perpendicular to that of the rotation axes, you're actually going to slice it down in such a way that you're unraveling the exteriors of it. So, for us to see this, determine the volume of the solid obtained by rotating the region y equals 1 minus x, y equals 0, and x equals 0 about the x-axis, or sorry, the y-axis. So, in this case, I'm going to go ahead and start by drawing the region. Y equals 1 minus x. So we're going to see a line that looks something like this. Y equals 0 looks like this. That's simply the x-axis. And x equals 0. Okay? So we have this triangular space right here. Okay, let me enlarge that, and again the idea is we're rotating around the y-axis, which means we're rotating around this line. So I'm going to see again that kind of object rotated around. When I redraw this, the idea is I'm going to have to slice this parallel with the rotation axes. So very carefully redrawing this object a little bit larger, reflecting it, and rotating it. Now you'll notice how I'm drawing these circles. I'm still drawing the circles horizontally in this case, but I don't want me to slice this with those circles. I want me to slice this against the circles. So again, think of it this way. I'm going to slice it right here, and then I'm going to go, actually let me try and slice it here to the best of my ability. I'm going to slice it right here, and in this spot right here, it's going to cut all the way down, and it's going to cut all the way down, and it's going to create this interesting can in the center. The problem is that the can itself is not being filled in, and the exteriors of this can have already been unraveled. Again, I want you to think of this object as though it's made of toilet paper, like we've chopped off edges of it, and we're simply going to unravel that toilet paper. Now, that can sitting in the center there, which I'm going to try and again darken in so it's easier for us to see it. That can is what I want to find the area of. Because if I can find the area of that can, then I can find the area of any other can that's in this object. For instance, this longer one here, if I were to cut that one down, again, there's a can, but that can, again, is just the surface area of that can. And again, I can do one out here, where I cut that one. And again, that one is going to have a different area. I want this function in this region right here to determine the areas of all of those cans unraveled. Now, if I were to slice down the edge of this can and unravel it, it would end up looking like a rectangle. So now, every single one of these cross sections that I cut this, where I cut it, again, parallel to the rotation axis, parallel to y-axis, we're going to end up finding that we're going to have a rectangle as the area. And the question is what is the area of any one of those rectangles? Well, this distance right here is going to be the height of that rectangle. Okay, that distance, height of the rectangle, is going to be this distance right here, or this one here, or this one here. The length of this rectangle will simply be the length of this circular cross section. But this circular cross section actually ends up being the circumference of a circle. So the circumference of a circle is simply 2 pi r. So our goal now is to figure out what r and what h are in this system. Okay? Now, very simply, the height. If I were to look at this object, the height is here, the height is here, the height is here, the height is here. The height is nothing more than the top minus the bottom of every single one of these already drawn lines. So the height is simply going to be, again, in general, top minus bottom. Just like we were trying to find the area of this region, it's just slightly different with the top minus bottom function. That's your height. Our r value actually relates the same way to the rotation revolutions in the washer or disk method. So the radius of this distance here will simply be, again, the same exact radius that we would have had to play with before. We're going to go ahead and pick a radius measure, and that radius measure is entirely dependent on either x or y. So if we had a different radius, not the x or y axis, it would simply be x plus y, x minus y, or some form, x plus r, x minus r, or some form of manipulation of that. Where in this case, my rotation axis is nothing more than the distance from this axis out to that point. That is r. But that distance right there, in the simplest sake, is nothing more than x. If we're rotating it around the y-axis, that is the equation x equals 0. If that's the equation x equals 0, then the rotation r value will always be r equals to x. So very carefully, I'm going to integrate over all of these different areas, where the area of all these cross-sections are 2 pi r each. So I'm going to go ahead and cut this region, very carefully cut this region vertically from x equals 0 to x equals 1, because again that intersection point is x equals 1, that intersection point is x equals 0. I'm going to go ahead and integrate over 2 pi r and h, and again I'm going to write this up here r, I'm going to write this h, and it's in terms of dx. So now I got to figure out what is r and what is h. Now r, again, we've already identified if we're rotating around an x or y axis, it's simply going to be the variable that the x equals 0 correlates to. So again, if this is x equals 0, or if this is y equals 0, x equals 0 we get x, y equals 0 we get y. So my r is simply x. My h is actually the height of this graph. And again, the height of this graph is simply the top of the function, which this is the top function, y equals 1 minus x, minus the bottom function. Well, the bottom function happens to be y equals 0. So the top function here is y equals 1 minus x. And I do 1 minus x minus 0 is simply 1 minus x. So very simply, this is the setup for the integral that calculates the volume of this cone object using rotations using shells. To evaluate this integral, you'll simply go ahead and factor the 2 pi out of the integral. You'll multiply this x into the pieces, x minus x squared dx. You'll evaluate the integral, x squared divided by 2, multiplied by 2 pi, minus x to the power of 3 divided by 3, evaluated from x equals 0 to 1. Plugging in 0 will give us 0, which is why I'm identifying it first. Plugging in 1 will end up with 2 pi times 1/2 minus 1/3 minus, and again I'm emphasizing the fact that when I plug in 0, I still get back 0. So whatever this happens to be, which ends up being 2 pi multiplied by, let's see, we get 3 minus 2, so 1 over 3, which is 2 pi over 3. This should be the exact same area. Actually, I'm sorry. This would end up being 6. Yes, 3 over 3, 2 minus 2. Yes, 1/6. So it ends up being pi over 3. This ends up being the exact same volume of that cone, assuming we did this utilizing the method of cutting it horizontally, trying to find those circular cross sections instead of these rectangular ones. Again, this is the volume integral. This should be the volume, and it shouldn't change depending on how we cut it. Should be the same volume.